Welcome back to another explainer, where today we're diving into the ultimate survival guide for tackling quantitative chemistry calculations. Look, the mole concept has a bit of a reputation, but it really doesn't have to be the monster it's made out to be. We're going to break down the exact strategies that take a confusing mess of numbers and turn them into a totally clear, logical path to the right answer.
So, think about this for a second. Why do so many of us absolutely bomb our mole calculations on exams, even when we have the formulas memorized backwards and forwards? I know, it's incredibly frustrating. But honestly, it's almost never because the math itself is too advanced. It's pretty much always because of a breakdown in the core rules of the game. We're talking mismatched units, forgotten conversions, and skipping those vital foundational steps. To defeat this topic once and for all, we're going to outline the rules. We'll quickly hit molar versus relative mass, look at calculating relative formula mass, dodge the volume conversion trap, walk through calculating mass concentration, and finally wrap up with common errors and sanity checks. Let's get right into it. Part 1, the ground rules. Specifically, the difference between molar mass and relative mass.
Now, this right here is our first major hurdle, and it's totally a conceptual one. You see, the numerical values for a substance might be mathematically identical, but the moment you include the grams per mole unit, well, it changes everything. Molar mass is a physical measurement, right? It's the actual mass of exactly 1 mole, that's 6.0 times 10 to the 23rd particles, of a substance. Because of that, you absolutely must write grams per mole. Relative mass, on the flip side, is just a ratio. It's a comparison, so it's completely dimensionless. If an exam asks for molar mass and you forget the units, boom, you lose the mark. If it asks for relative mass and you add units, you also lose the mark. It's that strict. And when we're talking about these ratios, there is a super common exam pitfall you need to watch out for. If you're ever asked to define relative atomic mass, you can't just casually say it's a comparison of masses. Nope. You absolutely must mention the carbon-12 isotope as the reference standard. It has to be compared to exactly 1/12 the mass of an atom of carbon-12. Leave that out, and your definition is incomplete. Okay, moving to part 2, the execution phase. Let's calculate relative formula mass. Since we've got the ground rules down, let's see how to actually calculate this without losing easy points. Take sodium chloride. It's a beautifully simple process. First, just pull the atomic masses right off your periodic table. Sodium is 23, chlorine is 35.5. Second, you add them together. And third, the absolutely crucial point here is that we leave our final answer of 58.5 completely dimensionless. Do not add a grams or grams per mole tag here. Adding units to this specific answer is a guaranteed way to lose marks, because as we just established, relative formula mass is just a ratio. All right, part 3. Enter the danger zone. I like to call this the volume conversion disaster. This is literally the #1 reason students crash and burn on mass concentration questions. Here is the setup. Exams love giving you concentration in cubic decimeters, which basically tells you how much mass is in a full liter of solution. But your actual test tubes, your lab beakers, and the specific volumes given in the math problem, those are almost always measured in cubic centimeters. So you have a massive mismatch in your units before you even pick up your pencil. Let's look at exactly what happens if you fall for this trap. Imagine a question asking for the mass of sodium chloride in 500 cubic centimeters of a solution with a concentration of 40 grams per cubic decimeter. If you just grab your calculator and multiply 40 by 500 without converting anything, you get 20,000 grams. I mean, think about that for a second. 20,000 grams is 20 kilograms. You're telling the examiner you have 20 kilos of salt in a standard lab beaker. That's 1,000 times too large. The actual correct answer is just 20 grams, which we only get by matching our volume units properly. 20 grams is a completely reasonable normal amount of salt to dissolve in half a liter of water. So please write this golden rule down somewhere. Memorize it, highlight it. You must divide your cubic centimeters by 1,000 to convert them into cubic decimeters before you even touch that concentration formula. Honestly, this single simple step is an absolute grade saver. Part 4, the playbook. Let's run through calculating mass concentration the right way. Let's put that golden rule into practice with a super rigid foolproof method. By compartmentalizing the math into 3 strict steps, you drastically lower your cognitive load. Step 1, isolate your knowns. What do you have? Step 2, handle the unit conversion immediately by dividing your volume by 1,000. Get it out of the way. Step 3, only now do you multiply the concentration by that newly converted volume. This structured approach literally prevents standard form errors and those annoying decimal slips. because you aren't trying to juggle everything in your head at the same time.
Let's actually test this workflow on a potassium chloride solution. Say we have a concentration of 60 grams per cubic decimeter, but we're only working with a tiny 25 cubic centimeter sample. Watch how isolating the conversion in step 2, taking that 25 and dividing by 1,000 to get 0.025 cubic decimeters, sets up the final calculation flawlessly. We then just multiply 60 by 0.025, leading us straight to the safe, mathematically sound, and correct answer of 1.5 grams.
Finally, part 5, the defense. Avoiding errors and running your sanity checks. Now, even with the perfect method we just walked through, you still need defensive strategies to protect your grade before you hand in that paper. Using basic proportional logic as a mental sanity check is your absolute best shield against simple calculator slips. Before you confidently box your final answer, pause. Just ask yourself, wait, does this actually make sense? If your concentration tells you there are 40 grams in a full 1,000 cubic centimeters, well, a 500 cubic centimeter sample is exactly half the volume, right? Therefore, it should have exactly half the mass, 20 grams. If you're dealing with 25 cubic centimeters, that's a tiny fraction of a liter, so your mass should be a tiny fraction too. If you somehow calculate 1,500 grams, you know immediately your decimal point has gone rogue. Before we wrap up, I want you to be aware of just a few more frequent pitfalls. We've hammered home the volume conversion trap, but examiners are also actively hunting for students who misplace decimal points or write completely unbalanced chemical equations, which, by the way, ruins your mole ratios entirely. They also look for ignored state symbols, like solid, liquid, gas, or aqueous. Plus, make sure your final answers have consistent decimal places. And whatever you do, please do not skip writing out your steps. If you make a tiny, silly math error, but your written steps prove you understood the process, you can totally still secure partial marks. The mole concept really doesn't have to be a monster, as long as you respect the units. It's just a game of rules, precision, and double-checking your logic. Thanks for hanging out with me on this explainer. I want to leave you with one final thought. The next time you're staring down a chemistry exam, will your units pass the sanity check, or are you going to let the volume trap catch you? And more importantly, what other hidden rules of chemistry are out there waiting to be decoded? Keep questioning the numbers, and I'll catch you next time.
Get more study resources at myteacher.net.